After centuries of research, scientists at CERN have made a discovery that completely overturns our understanding of the laws of physics. The implications of this startling new finding for our planet's future are enormous. The European Organization for Nuclear Research, or CERN for short, is the world's largest facility dedicated to the study of subatomic particles. Located in the Swiss countryside not far from Geneva, it was founded in 1954 as one of Europe's earliest cooperative ventures in the wake of World War II, with the intention of stemming the flow of bright minds to the U.S. Every year, CERN hosts over 10,000 researchers from over 100 different nations to use its state-of-the-art facilities, which house some of the world's largest and most sophisticated scientific instruments. The group's objective is to learn more about the nature of the universe and the physical principles that govern its functioning. How does the Large Hadron Collider function, and what is it? The Large Hadron Collider, LHC, is the world's most powerful particle accelerator, a massive machine used by physicists to crash subatomic particles together at high speeds. For a split second, the particle collisions mimic the conditions just after the Big Bang, when the universe was born. The physics community investigates fundamental questions, such as the nature of matter and the origin of particle mass, by analyzing the remnants of these collisions. It was with the express purpose of testing the standard model of particle physics that the LHC was constructed in 2008. Extremely popular in the 1970s, this theory explains how electromagnetism, the strong nuclear force, and the weak nuclear force interact with the 17 known basic particles and the other two fundamental forces of the universe. Gravity is the fourth. The Higgs boson, a fundamental particle never before observed, has long been postulated by the Standard Model. Using the LHC, physicists finally found it in July 2012, after 40 years of seeking. This revelation was a huge victory for proponents of the Standard Model, but the theory itself remains unfinished. As an example, it doesn't answer the question, what is dark matter? How come there's not as much antimatter as there is matter in the cosmos? To some extent, the LHC could shed light on these mysteries. The apparatus is hidden in a circular tube almost 27 kilometers long beneath the France-Switzerland border close to Geneva. More than 1,035-ton superconducting dipole magnets, cooled to minus 271.3 degrees Celsius, colder than outer space, is used to steer two streams of particles, often protons, in opposite directions around the ring. At a rate of about 11,000 circuits per second, the protons race around the 27-kilometer ring at nearly the speed of light. The two beams are angled so that they intersect 4 times around the ring. Protons within the beam collide and break up into smaller fragments at the intersection points. The vast majority of the particles created by the collisions are extremely unstable and quickly transform into less dangerous forms. 7 massive detectors, the size of cathedral-sized digital cameras, are constructed around the 4 collision zones to record information about these extremely rare particles during their brief but intense bursts of creation. Scientists have made the first detection of ghost particles or neutrinos inside an atom smasher at the Large Hadron Collider. The LHC at CERN near Geneva, Switzerland, the world's largest particle accelerator, detected the subatomic particles during a new detector's trial run. This is not only the first time neutrinos have been seen within the LHC, but also the first time they have been found inside any particle accelerator, according to a research published on November 24 in the journal Physical Review D by the Forward Search Experiment Collaboration at CERN. Because of this development, scientists now have a new way to peer into the realm of subatomic particles. University of California Irvine physics professor and co-leader of the Phaser team, Jonathan Fang, said in a statement, "Before our effort, no trace of neutrinos has ever been discovered at a particle collider. This major discovery helps researchers learn more about the nature of these enigmatic particles and the cosmic function they play. Approximately 100 billion neutrinos permeate your body's 1 square centimeter every second. These subatomic particles are ubiquitous, being created in particle accelerators and nuclear reactors on Earth, as well as in the nuclear inferno of stars and in gigantic supernova explosions. Yet despite their prevalence, the particles continue to elude capture. Neutrinos hardly interact with regular matter since they have no electric charge and almost no mass. Neutrinos live up to their ethereal moniker by treating ordinary stuff throughout the cosmos as if it were not there and zipping through it at nearly the speed of light. To be sure, neutrinos are difficult to capture, but it doesn't mean it's impossible. Indirectly, through a process called Cherenkov radiation, Some of the most well-known neutrino detection experiments have observed solar-generated neutrinos. These include the Japanese Super Kamiokande detector, the Fermilab Mini Bu NE detector, and the Antarctic Ice Cube detector. A sonic boom is produced when an airplane travels faster than the speed of sound, and a faint blue glow is produced when a particle travels faster than the speed of light through a medium that slows light, such as water. Scientists can detect the trails of particle byproducts formed when neutrinos impact an atomic nucleus head-on by looking for this glow. Subatomic ghost particles. Still on the hunt, scientists have been constructing an observatory in the most hostile region on Earth for almost a decade in an effort to find a ghost. As a huge telescope, the Ice Cube Neutrino Observatory may be found buried in the ice of Antarctica, not far from the South Pole. Despite their success in identifying solar neutrino signatures, such studies tell us surprisingly little about the types of high-energy neutrinos created when particles collide in particle accelerators. The Phasor-Nu detector was developed by the Phasor Consortium in order to detect these naturally occurring neutrinos. Like a particle-detecting s'more, the Phasor-Nu consists of heavy metal plates of lead and tungsten sandwiching layers upon layers of light-detecting gunk called emulsion. As a first step, neutrinos produce particle byproducts when they collide with atomic nuclei in the dense metal plates. Then the emulsion layers react with the neutrino leftovers to imprint the traced outlines of the particles as they zip through them, just like the old-fashioned photographic film, says Feng. It was only after developing the emulsion and analyzing the particle trails left behind that the physicists were able to discover that some of the markings were caused by neutrinos, and more specifically, that they were caused by one of the three neutrinos' flavors, tau, muon, or electron. This proved that the researchers had chosen the optimal location within the massive 17-mile ring in which to detect neutrinos, and that their new detector was really sensitive enough to pick them up. The physicists have started construction on a larger version of the detector they believe will be able to tell the difference between neutrinos and their antimatter counterparts, antineutrinos, and will be far more sensitive to finding the elusive particles. When the LHC restarts in 2022, scientists will utilize the detector to investigate the neutrinos it generates. We anticipate recording around 10,000 neutrino interactions in the next run of the LHC, which will begin in 2022, thanks to the power of our new detector and its prime location at CERN, as stated by Casper. The most powerful neutrinos ever created by humans will be detected by us. However, neutrinos aren't the only prey of the Phasor researchers. Dark matter, a mysterious non-luminous element that is thought to account for around 85% of the stuff in the universe, is thought to be intimately tied to hypothetical dark photons, which the team is also seeking to detect. And that brings us to the end of this video. Feel free to let us know what you think about this video. And if you liked this video, then please leave a like and subscribe to our channel for more amazing content. Thanks for watching, and we'll see you in the next one.